I want us to look at Kohlrausch's law. It's called Kohlrausch's law of independent migration of ions. Then later we shall see its application in our next lesson. But for today, let me introduce something about it. This law was investigated or was brought about by a scientist called Kohlrausch. That's why it was named so. Kohlrausch Friedrich. When he studied molar connectivity at infinite dilution of very many electrolytes. After making a good study of molar connectivity at infinite dilution of very many electrolytes, he found out that the molar connectivity at infinite dilution of every electrolyte he studied was a sum of two quantities. It was a sum of the ions that electrolyte contains. For example, after a good study, Kohlrausch found out that molar connectivity at infinite dilution of sodium chloride was the molar connectivity at infinite dilution of the sodium ion added to the molar connectivity at infinite dilution of the chloride ion. Briefly, that's what Kohlrausch found out. And from that, he stated the law. He said that the molar conductivity, the law states that the molar conductivity at infinite dilution of an electrolyte is equal to the sum. Molar conductivity at infinite dilution of an electrolyte is equal to the sum of the molar conductivities at infinite dilution of ions produced by the electrolyte. It is very simple. It's the simplest law to state in chemistry. Kohlrausch's law states that molar connectivity at infinite dilution of any electrolyte is equal to the sum of the molar conductivity at infinite dilution of the ions produced by that electrolyte. And for that, we can have a variety of examples. If I want molar conductivity at infinite dilution of magnesium chloride, it will be the molar conductivity at infinite dilution of the magnesium ion plus twice the molar conductivity at infinite dilution of the chloride ion. Why twice? Because magnesium chloride has two chloride ions. You should be very careful with the formulae here, depending on the electrolyte you have. If I want molar conductivity at infinite dilution of sodium sulfate, it will be molar conductivity at infinite dilution of twice the molar conductivity at dilution of the sodium ion, because I have two sodium ions here, plus the molar conductivity at infinite dilution of the sulfate ion. If I want the molar conductivity at infinite dilution of calcium phosphate, it will be thrice the molar connectivity at infinite dilution of the calcium ion plus twice the molar connectivity at infinite dilution of the phosphate ion. To the 2 phosphate ions and 3 calcium ions I do have here. If I want the molar conductivity at infinite dilution of ethanoic acid, it will be molar conductivity at infinite dilution of the ethanoate ion plus molar conductivity at dilution of the hydrogen ion. So briefly, that is Kohlrausch's law. Where can it be applied? I will just mention the applications, and then I will see only one of them in this particular lesson. So where do we apply Kohlrausch's law? The applications are about 4 of them. The first one is indirect determination of molar conductivity at infinite dilution for weak electrolytes. Indirect determination of molar conductivity at infinite dilution for weak electrolytes. That's one application. The other one is to determination of solubility. Remember, in ionic equilibrium, we looked at this. You saw me applying some formula involving molar conductivity at infinite dilution to determine the solubility of sparingly soluble electrolytes. It is also applicable in determining not only its solubility of sparingly soluble salts, but in determination of the solubility product of sparingly soluble salts still. It is also applicable if you want to determine the degree of dissociation. We shall look at each of these: the degree of dissociation and equilibrium constant of the weak electrolyte. It is finally applicable in what we call indirect determination. We have already looked at it. It's indirect determination of molar conductivity and dilution for weak electrolytes. For today, I want us to look at this specifically. How do you use Kohlrausch's law to indirectly determine molar conductivity at infinite dilution for a weak electrolyte? Now, if you want to determine molar conductivity at infinite dilution of any weak electrolyte, we may obtain it indirectly using molar conductivities at infinite dilution of strong electrolytes. For example, I may want to determine molar conductivity at infinite dilution of ethanoic acid. But ethanoic acid being a weak electrolyte, it's not easy to measure its molar conductivity. However, if I have strong electrolytes, for example, I have a strong electrolyte like sodium ethanoate, and I know maybe its molar conductivity at infinite dilution. And maybe I also know the molar conductivity at infinite dilution of hydrochloric acid. I have hydrochloric acid and I know its molar conductivity at infinite dilution. I also know the molar conductivity at infinite dilution of maybe sodium chloride. I also know the molar conductivity at infinite dilution of sodium chloride. I can use these three molar conductivities to obtain the molar conductivity at infinite dilution of ethanoic acid. How do I do that? I'll say I'll use these three and see how can I get an equation generating ethanoic acid from them. How can I get an equation that can help me generate ethanoic acid from them? But that equation is side work. It's not important to me. It's not so important to me. So how do I do that? I want to get ethanoic acid from these ones. Ethanoic acid is got by the reaction between or I can get sodium ethanoate by the reaction between ethanoic acid. We have this equation. React ethanoic acid with sodium. React ethanoic acid plus which compound here? I may not be able to react. So I may not get it by an equation, but necessarily I have to play around with these values. How can I play around with them to get molecular dilution of ethanoic acid? Look at sodium ethanoate. This one is specifically equal to the molar conductivity of ethanoate ion, according to Kohlrausch's law, plus molar conductivity at infinite dilution of the hydrogen ion. I think you are aware of that. Then where do I get the ethanoate ion from? I get it from here. So to simplify my work, I will say molar conductivity at infinite dilution of ethanoic acid will equal to the molar conductivity at infinite dilution of the ethanoate of the sodium ethanoate. Because from the sodium ethanoate, I want the ethanoate ion from there. Then where do I get the hydrogen ion from? It will be from hydrochloric acid. So that will be molar conductivity at infinite dilution of hydrochloric acid. When I add the two, there is sodium chloride incorporated in my work. So that one I subtract it off, molecular dilution of sodium chloride. That's the only clue that you need to understand. Okay? It's the only clue that you need to understand. So you have to play around with these values to see how you get your final answer. If that one is a bit disturbing, let us do the derivation. Where does it come from? We can write molar conductivity at infinite dilution of each of them. The molar conductivity at infinite dilution of sodium ethanoate is equal to the molar conductivity at infinite dilution of the ethanoate ion plus molar conductivity at infinite dilution of the sodium ion. Molar conductivity at infinite dilution of hydrochloric acid is equal to molar conductivity at infinite dilution of the hydrogen ion plus molar conductivity at infinite dilution of the chloride ion. Molar conductivity at infinite dilution of sodium chloride is equal to molar conductivity at infinite dilution of sodium ion plus molar conductivity at infinite dilution of the chloride ion. Now, if I want that of ethanoic acid, I obtain it by adding this equation to this one and subtracting off the third one. So that means molecular connectivity addition of ethanoic acid will equal to this one added to this one, and then subtracting off this one. When I add these two, I already have the ions I'm interested in, but I'm introducing the sodium chloride, which I don't want. That's why I subtract off the third, remove this one. So you still go back to your initial equation, which is this one. So I'm introducing this because you're going to be using it in calculations. Let's see an example. Let's see some two examples here. The first example is below molar conductivities. At infinite dilution of some electrolytes. We have the electrolyte, then molar conductivity at dilution, units S centimeter squared per mole. The first one is sodium chloride. They may be given to you as words to see whether you can write the correct formula, 113. The other one is ammonium chloride. And that one is 134.1. The other one is sodium hydroxide. And that one is 225.2. The other one is sodium methanoate. And that one is 101.2. And the last one is hydrochloric acid. That one is 397.8. If we have those electrolytes with us, we can be asked to calculate. Question says, calculate. And Roman 1 is calculate molar conductivity at infinite dilution of, the first one is methanoic acid. So how do you get molar conductivity at dilution of methanoic acid? Methanoic acid is this acid here. So if you want its molar conductivity at infinite dilution, the formula you will use is molar conductivity at dilution of the methanoate ion plus molar conductivity at dilution of the hydrogen ion. So you have to play around with the values that you're given and see where you get the methanoate ion and hydrogen ion from. So the equation I will use here will be molar conductivity at dilution of methanoic acid will equal to the molar conductivity at dilution of what? When I look at my values here, I can get methanoic acid. It's not given anywhere here, but I can get it from sodium methanoate. From sodium methanoate is this compound. From it, I get the methanoate ion. Then from hydrochloric acid, I'll get the hydrogen ion. But I introduce sodium and chloride ions, so how do I remove them? Then I subtract it off that of sodium chloride. Let me hope you're getting me. So I will say molar conductivity of methanoic acid at infinite dilution or zero concentration is equal to molar conductivity at infinite dilution of sodium methanoate, which I have in the table, plus molar conductivity at infinite dilution of hydrochloric acid. These two, when added together, give me the methanoic acid. So I subtract off the sodium chloride molar conductivity. And when I substitute it in my values, I will get the answer. That of sodium methanoate is 101.2. That of hydrochloric acid is 397.8. And that of sodium chloride is 113. The final answer here is 386 S centimeters squared per mole. That's the molar conductivity at dilution of methanoic acid. I may ask you to get molar conductivity at dilution, Roman 2, of ammonia solution. Talk of ammonia solution, that is ammonia. Ammonia solution is ammonia in water. So when ammonia is in water, it forms ammonium ions and hydroxide ions. So those are the ions you shall look for. So what will be my answer? I'll say molar conductivity dilution of ammonia solution, ammonia aqueous, will equal to the molar conductivity dilution of what? Where is anything related to ammonia? I have ammonium chloride. That's where I'll get the ammonium ion from. Plus molar conductivity dilution. Now I need the hydroxyl ion. Ammonia aqueous is what you hypothetically call ammonium hydroxide. But for us, we write it as ammonia aqueous. So where shall I get the hydroxide ion? The hydroxide ion will be got from sodium hydroxide. So this will give me ammonium hydroxide. Then I've introduced the sodium chloride, subtract it off. Molar conductivity dilution of sodium chloride. Some of you, when you're writing this formula, you forget this symbol for molar conductivity dilution. That makes you lose marks. So you must write the correct formula because we are dealing with molar conductivities and at infinite dilution, so the note should be there. When you don't put the note, then you're not talking of molar conductivity at infinite dilution. So what shall I have in this case? That of ammonium chloride is 134.1. That of sodium hydroxide is 225.2. And that of sodium chloride is 113. The answer here is 246.3 S centimeters squared per mole. If I want molar conductivity at infinite dilution, I can ask you to calculate that of maybe ammonium methanoate. So what shall I do to get molar conductivity at infinite dilution of ammonium methanoate? Ammonium methanoate is written like this. This is ammonium methanoate. So its molar conductivity at infinite dilution, you can see it from here, that it will equal to that of methanoic acid plus that of ammonium chloride. That's where I get ammonium methanoate, then minus that of sodium chloride. So that of methanoic acid is already got. We have already calculated it. Is that okay? Actually, I may not use that of methanoic acid because I don't have it in the table. In the table, what I have there is sodium ethanoate, sodium methanoate. Sorry for this mistake. This is sodium methanoate, which is now 101.2 plus 134.1, then minus 113. So that gives me 122.3 S centimeters squared per mole. Now, part B of this question is to ask you to explain the difference in your answers in A1 and 3 above. This is Roman 3. It's molar conductivity of sodium ammonium methanoate. Roman 1 was molar conductivity of methanoic acid. So molar conductivity of methanoic acid at infinite dilution is which value? The value we have calculated is 386. Let me leave the units for now. That of ammonium methanoate is 122.3. So they want you to explain that difference. First of all, state the difference. What's the difference that you're stating? The difference is that the molar conductivity at infinite dilution of methanoic acid is higher than that of ammonium methanoate. That's the difference, first of all. Then what causes that difference? The difference is here. You see, this is methanoic acid and this is ammonium methanoate. Both of them have the methanoate ion, but the difference is between the hydrogen ion and ammonium ion. So the reason as to why ammonium methanoate has a higher conductivity is due to the hydrogen ion in it, whereas here there is the ammonium ion. The hydrogen ion is more conducting or has a higher molar conductivity than the ammonium ion. So you're going to say this is because the hydrogen ion in methanoic acid has a higher molar conductivity than the ammonium ion in ammonium methanoate. All right. So that's all about the explanation. Let me see one more example about indirect determination of molar conductivities for weak electrolytes. And that will be my last example about this. Question says, the molar conductivity at infinite dilution of the sulfate ion is 160 per ohm centimeter squared per mole. If the molar conductivity at infinite dilution of the sulfate ion, of aluminum sulfate, sorry, is 858 per ohm centimeter squared per mole. Calculate the molar conductivity at infinite dilution of the aluminum ion. This is a very good question, but can be easily done. So what do? We are given molar conductivity of the sulfate ion We also given molar connectivity of aluminium sulfate. They want that of the aluminium ion. So you simply write our equation according to Kohlrausch. So we say from Kohlrausch's law, molar connectivity and dilution of aluminium sulfate the correct formula should be written. If you have a wrong formula, you don't get a correct answer. Will equal to twice molar connectivity and dilution of the aluminium ion. Why twice? If aluminium ion is here, plus thrice molar connectivity and dilution of the sulfate ion. Then substitute what you're given. That of aluminium sulfate, we have it as 858. We don't have that of the aluminium ion. We have that of the sulfate ion as 160. So the molar conductivity at dilution of the aluminium ion will obviously be this value, which is 858 minus 3 into 160 divided by 2. And your answer from that will be 189 per ohm, centimeters squared per mole. Thank you for attending this lesson. Our next lesson will be looking at how we use Kohlrausch's law to determine solubility and solubility product of sparingly soluble salts. That one also involves a number of calculations that we didn't see in ionic equilibria. And then after seeing that, we shall also see how do we use it to obtain degree of dissociation and equilibrium constant. And then we shall see how to apply conductance. We have been studying conductance. Where is it applicable? We shall see the conductimetric titrations, and then I'll introduce you to electrode potential and electrochemical cells. See you then. Watch more of our videos, but don't forget to subscribe. Bye-bye.